Hello everybody, my name is Boro Sofrananc and today I will present you a paper co-authored by Ambros Gleixner, Sebastian Pokut and myself. The paper deals with a GPU parallel algorithm to perform domain propagation. Let's dive right in. Before defining what domain propagation is, I first have to tell you about mixed integer linear programming, or MIP for short. MIP is the problem of minimizing a linear objective function such that a solution fulfills a given set of linear constraints. Each variable in the problem has a lower and a upper bound, and some of the variables are restricted to only take integer values. Solving MIPs in theory is NP hard, however, surprisingly fast solvers have been developed in practice. Most of them use a core algorithm known as branch and bound, and then supplemented with various extension techniques that speed it up. The first step of this algorithm is the branching step. In this step, the problem is split into several subproblems, which are hopefully easier to solve. The most common way to branch is to divide a domain of a variable in two or more subdomains and then treat each of those as individual problems. By doing this repeatedly, a so-called search tree is obtained, which is depicted here on the right. The bounding step solves relaxations of the problem at each node in order to obtain lower bounds on the objective function value. This is then used to prune suboptimal nodes, which cannot lead to improving solutions, thus avoiding enumerating exponentially many subproblems. The most common way to obtain a relaxation of a problem at a given node is to drop the integrality constraints, at which point a linear program is obtained. This can be solved by, for example, the simplex method. Domain propagation is one of the most important supplementary techniques that MIP solvers use to speed up the solution process. The core idea of this technique is to eliminate parts of domains of each variable that cannot lead to feasible solutions of the problem. MIP solvers apply this technique to the original problem in the so-called pre-solving step, but also during the solving process at each node of the search tree. I will use this toy example you see on the slide to introduce the idea of domain propagation. We have a constraint which consists of three variables, and each variable has its lower and upper bounds. Let's first focus on the upper bound of variable 1. Even if the sum of the remaining variables takes its minimum value, which in this case is -2, x1 cannot take values larger than 3 without making the constraint infeasible. This is because it would violate the right-hand side. We conclude that x1 has to take values less or equal than 3. Similarly, we can repeat the process for the lower bound. We would now look at the maximum value of the sum of remaining variables and conclude that x1 has to always be greater or equal than -3. If we generalize this process to arbitrary linear constraints, we get a formula as you see on the slide. The exact algebra is not important for our discussion. Just note that the upper and lower bounds are a function of the left and right hand sides of the constraint, the betas in this notation, constraint coefficients A, J's, current lower and upper bounds of the variable in question, and the generalization of the concept of minimum and maximum value of the sum of remaining variables, which are called the minimum and maximum activities. These formulas are applied to each variable of the constraint and each constraint in the system. When it happens that several constraints share the same variable and the bound of that variable changes, we have to reapply these formulas to those constraints, which gives the domain propagation its iterative nature. This algorithm can be seen as a fixed point iteration, and as such, it has a unique greatest fixed point. However, it might not converge to this fixed point in finite time. To deal with this effect, most modern solvers impose tolerance-based termination criteria which stop the algorithm when the newly found bound changes become too small. This paper aims at developing an algorithm which will run on GPUs. GPUs are highly specialized hardware originally developed for graphics processing. By today, they have evolved into general-purpose computing platforms. The schematic representation of a GPU and a CPU chip you see on the slide highlights the differences in how GPUs and CPUs use their hardware resources. The portions of the chip colored green are data processing units. You can see that GPUs devote a much higher portion of their chip to this. However, this comes at the expense of, for example, control execution units, shown in yellow color here. This leads to a highly specialized programming model on the GPUs, which is not as flexible as programming models for CPUs. We will have a lot of computational power on our hands, as GPUs routinely offer thousands, if not hundreds of thousands of parallel threads, but exploiting this power will require adhering to the constraints of its programming model. Because of this, algorithmic design decisions made for an algorithm running on CPUs will often be different to those made for the execution of the same algorithm on the GPUs. Modern MIP solvers today do not use GPUs in their solving process. Some of the major challenges are that the data structures that MIP solvers operate on are very sparse and irregular. This is coupled with often very non-uniform behavior of the developed algorithms. On top of this, many of the existing algorithms were designed with having a sequential execution model in mind, which does not allow to transform them easily to an efficient GPU implementation. I will now talk about some of the features of sequential implementation of the propagation algorithm and the challenges that these pose for efficient GPU implementation. Let's first look into a feature called constraint marking. This allows the solver to mark constraints which can possibly lead to new bound changes and disregard the rest. This is based on the fact that from one iteration to another, only those constraints that contain a variable whose bounds have changed can possibly lead to a new bound change. This process is depicted on the figure you see in the middle. X's represent non-zeros of the constraint matrix. The red constraints are marked, while the black ones are not. The left side depicts the first iteration of the algorithm when all constraints are marked. Assume that the only bound change found during this iteration is a bound of a fourth variable here. In the next iteration, we would have to consider this constraint together with the first and the last constraint, which also contain the variable. This is shown here on the right. The important thing to notice is that we don't know a priori which variables will produce bound changes, and hence we don't know which subset of constraints will be marked. This means that random memory locations will be accessed, potentially those far apart. This would lead to poor memory coalescing and decreased GPU performance. Next, because the size of the process set of constraints changes both in size and content, achieving good load balancing and hardware utilization is challenging. Potentially, one would have to redistribute the work to available threads after each iteration, which imposes a sequentialization point in the algorithm and in our experiments has led to significant performance degradation. Another feature which helped the sequential algorithm avoid redundant work are the early termination checks. I will explain how these work with the help of the figure you see in the middle. As before, the X's represent the non-zeros. The circles represent the steps the algorithm needs to take in order to compute a possible bound change. The size of the circles represents the amount of computational effort each step requires. Different steps often require different amounts of work. After each step, there are some algebraic checks which can detect the case when no bound change is possible for this variable. If this is the case, the sequential algorithm stops processing this variable and moves on to the next one. In our example shown in the figure, circles colored red are the process steps, while the rest are skipped. As before, we don't know a priori which steps will or will not be taken. In the sequential execution, this does not affect the algorithm, which benefits from less work. But on the GPU, such behavior would be very challenging to implement in a way that all threads get equal amounts of work. The two features I presented are very beneficial for the sequential execution, but we have to rethink whether they make sense in the massively parallel GPU model. In our paper, we proposed that removing these features altogether benefits the GPU algorithm. Additionally, removing these features allowed us to change the way the propagation algorithm progresses through the computation in a way that maximizes throughput and leads to uniform step sizes in any given moment, solving the load balancing problems we had before. I will explain this in more detail with the help of the figure you see on the slide. On the left, the workflow of the sequential algorithm is shown. It starts with the first non-zero and executes as much as possible for that non-zero. Then it takes the second non-zero and does as much as possible for that, and so on. Each color represents one step of the algorithm, and you can think of the amount of each color as of the amount of work invested in each step. On the right, you can see the workflow of the GPU-based algorithm. Instead of taking a non-zero and going as far as possible with the computation, it instead takes the first step and then computes this for all the possible non-zeros. Then it takes the second step and computes that for all the non-zeros, and so on. As the figure depicts, we now have a static distribution of equal amounts of work at each step of the algorithm. An analogy I find useful that captures the shift I described is the difference between the depth-first search and the breadth-first search of a tree. We started with something akin to depth-first, going down a chosen path as far as possible, and then switched to a breadth-first with exploring everything possible at a given level before going down to the next level. In the end, we have a trade-off. We get a well-structured, static execution, but we have to do more work. Because this allows us to unlock the massive amount of parallelism the GPUs offer, this trade-off will work in our favor, as our results will show later. I will now talk a little bit about how we handle the irregular sparse structure of the constraint matrix in our algorithm. I will introduce the idea of the computation of minimum and maximum activities. The rest of the computation will extend naturally from there. Activities can be computed by the formulas you see in the middle. The key observation for efficient implementation of these on a GPU is that it is conditioned by the same factors that condition efficient implementation of sparse matrix vector products, or SPMVs. With this in mind, we will be able to carry over the ideas developed for SPMV algorithms and adapt them to the computation of activities. Our observation is based on the fact that doing SPMVs on the GPUs is highly bandwidth bound, meaning that memory access patterns will play a crucial role in the implementation. If you look at the formulas, you can see that the arithmetic operations to do a matrix vector product and to compute the activities differ. However, let's look closer at needed memory. If the coefficient AI is greater than 0, then the lower bound will be used in the computation of the minimum activity, and the upper bound will be used in the computation of the maximum activity. Likewise, if a coefficient is smaller than 0, then the upper bound is used for the computation of the minimum activity, and the lower bound is used for the computation of the maximum activity. So to compute activities, we have to access the coefficients and the vector of lower and upper bounds exactly once. This is exactly the same as if we were computing a matrix vector product of a matrix A with the two right-hand sides vectors. The SPMV algorithms we will need are CSR vector and CSR stream. I will introduce their core ideas together with the CSR scalar algorithm. On the left-hand side of the figure, you can see the non-zero elements of a constraint matrix. On the lower right, you can see a representation of how these would be stored in memory in the CSR storage format. On the upper right, you can see a representation of two thread blocks on the GPU, each consisting of a number of threads inside. These threads are grouped into so-called warps. The CSR scalar algorithm assigns one thread per constraint of the matrix. Let's see how the access patterns look like. The first thread would access the first element in the first array. The second thread would access the first element in the second array, and so on. As you can see, this would result in strided memory accesses, as neighboring threads would not be accessing neighboring locations in memory. This would degrade the performance of the GPU implementation. The CSR vector solves this problem by assigning a warp of threads per constraint. This way, the first thread accesses the first element in the first row, the second thread the second element in the same row, third thread the third element in the same row, and so on. This results in fully coalesced memory accesses as neighboring threads access neighboring elements. However, if there are more threads in the warp than there are non-zeros in the constraints, this would leave some of the threads idle, resulting in poor load balancing. The core idea of the CSR stream is very simple. It groups constraints that have only a small number of non-zeros together in blocks, and then assign one thread block per a block of constraints. This way, we are still accessing memory in the coalesced way, but we have solved the problem of idle threads for sparse constraints. Let's now have a look at what the sparsity pattern of an example MIP problem looks like. You can see that on the figure on the left. This matrix is clearly very sparse overall. However, notice that there are a few very dense rows in the top. This is a common occurrence in MIP matrices. These constraints are called connecting constraints. Thus, it will be crucial for our algorithm to be able to handle well both very dense and very sparse rows in the same matrix. You can see a high-level pseudocode of the final algorithm on the listing on the right. It first looks at how the constraint matrix was blocked. If we have more than one row in the block, we apply the algorithm based on the CSR stream to compute the activities. In case of very dense rows, where there is only one row in the block, we apply the CSR vector-based algorithm. Additionally, for extremely dense rows, we allow the CSR vector to use all the threads in the thread block as opposed to only the threads in a warp. After that, the algorithm keeps the same distribution of threads per non-zeros of the matrix and computes the new bound candidates for each non-zero in the matrix. At this point, we have to update the bounds of variables if the newly computed candidates improve on the old bounds. Our best performing variant uses atomic operations to do this. As we will see in the results section, we also tested a reduction-based variant which first saves all the candidates in global memory and then performs a reduction on them. To test our implementation, we used the MIPLib 2017 test set. This test set is de facto standard for MIP solvers. It contains both very small and very easy, as well as very large and hard problems. We removed the smallest of the instances from the test. For these, there is no motivation to replace the sequential algorithm, nor is there enough parallelism for the GPU to exploit. Additionally, to be better able to gauge the effect of the size of the instance on the algorithm, we divide the rest of the instances into 8 subsets of increasing size. In terms of hardware, we tried our implementation on 5 machines. First, we have the 2 high-end CPUs, a 24-core Intel Xeon machine and the 64-core AMD Ryzen. Then we have the 2 high-end GPUs, the NVIDIA Tesla V100 and the NVIDIA RTX. Lastly, we also use the low-end consumer-grade Quadro P400 GPU that is often found in home-use desktops. We tested 4 algorithms. First, just the sequential implementation that closely follows the algorithms found in modern MIP solvers. Second, we implemented the same algorithm in parallel with OpenMP using CPU shared memory. Lastly, we have the 2 GPU algorithms we already discussed, the atomic and the reduction-based kernel. As the metric for comparison, we use speedup over wall clock time for propagation to the fixed point. We chose the sequential execution running on the Intel Xeon machine as the base case, and we will report the speedups for the rest of the algorithm machine combinations over this execution. The figure on the left shows geometric means of speedups over the 8 subsets of increasing size for each algorithm machine pair. First, we can see that the 2 high-end GPU executions, colored red and blue, drastically outperform the CPU and low-end GPU executions. The top-performing Tesla V100 atomic run starts at 1.6 times the speedup over the base case for the smallest test set 1 and achieves a mean 46 times speedup over the base case for the largest set 8. At the same time, we can see that the low-end GPU, colored green, does not offer enough resources to exploit the parallelism. It performs similarly to the base case with the atomic kernel and underperforms with the reduction kernel. Given that GPUs are not used by today's MIP solvers, we believe that this is an interesting result in itself, as even for the consumer-grade home-use desktop machines, this algorithm can be competitive with its CPU counterparts. Lastly, notice that the OMP executions showed in dotted lines also significantly underperform compared to the 2 high-end GPU executions. The relatively high cost of managing CPU threads proves not to justify the low arithmetic intensity units of work that it does in parallel. This is especially visible for the first 4 sets. The figure on the right shows speedups over all the instances in MIPLib sorted in ascending order. We can see that the top-performing GPU algorithm has a steeper curve, meaning that it better responds to the increase in parallelism. Additionally, it wins over the base case for about 85% of instances. For favorable large instances, the speedups go as high as 195 times. With that, I would like to conclude this presentation. Thank you for your attention.